right. Hi, everyone. Welcome to Ops Lecture 7. We've already done 7 lectures so far. This is amazing. And it's still week 3 because it's on a Sunday. If you're watching this later, you're probably in week 4. So welcome. So your iPadrino music competition submissions we've gotten, and we're going to go over them after this lecture today and choose the top 3. And then you guys will be able to vote on those top 3, and the winner will get some gift cards, Amazon gift cards. So that's coming. And then we have additional parts coming in as well, as we announced earlier on Facebook and stuff. We got your addresses, so we're just waiting on one part of our many parts to arrive before we can send them out to you. So once those arrive at your doorsteps, you'll be able to do these projects that are going to be fun. Yeah. So today we're going to talk about capacitors. Ooh. And then integrated circuits and the 555 timer.
Yes, so let's get started about capacitors. Capacitors are usually like the second component you learn after a resistor, but they're kind of tricky to think about it. So what is a capacitor? Fundamentally, it's two conductive plates, so usually some kind of metal, that are separated at some distance. And what this causes is that current can't flow directly through, like in a wire. And over time, as you apply a voltage, a charge builds up in it. And this sort of gives name to capacitance. And capacitance tells you how much charge can be stored inside a capacitor. So one way to think about it is like water buckets, because when you fill it up, it's like the current can flow through, but eventually it caps out at something. And that's proportional to the capacitance. So once it caps out, water can't flow through anymore.
Yeah, and actually the capacitance of a capacitor depends on the physical structure of the capacitor. So if you have bigger plates, you have more capacitance. If the plates are closer together, you have more capacitance because the field between them becomes stronger.
So a lot of times when you think about capacitors, you think of them as either charging or discharging. So opposite charges accumulate on each of the plates. So one side will be positive, one side will be negative. As this charge accumulates, the voltage across them increases. Whenever the capacitor is fully charged, what that means is that the voltage across the capacitor is equal to whatever the source is that's being applied. So if you're applying 5 volts to a capacitor, when it is fully charged, it'll have 5 volts in it, or across it rather. And when it is fully charged, no more current can pass through it. So it essentially stops the flow of current and it's capped out at that 5 volts. All right. So now we are going to do a couple poll questions. So the first one is, let's say that we have this circuit here being described. And on the left, it's showing that there's a 12-volt difference there. So you can imagine a 12-volt battery. The first question is asking, let's say we switch it into position A. What is the voltage across the capacitor after a very long time?
And then the second question asks, if we flip the switch to B, what is the voltage across the capacitor after a very long time? And if you don't know anything, just like put your best guess in. You're not expected to know anything. Capacitors are fun. Right, waiting on a couple more of you. I'll give you 15 more seconds. What will the voltage across be? All right, I'll end the poll.
Yeah, so a lot of you guys got both of them right. So let's talk about the first one real quick. So what happens is when you first switch it into position A, current starts flowing and then it builds up a charge over time. After a very, very long time, what happens is all the charge is fully stored in there. And like we said, once that's complete, the voltage across the capacitor is same as the applied voltage. So it should be equal to 12 volts. When you switch it into B, all that charge is now going to discharge. So as soon as you do that, it's going to start powering this lamp here. Depending on the capacitance, sort of depends on how long it'll keep the lamp on, but eventually all that charge will run out and it'll go back down to 0. If you notice this question, we gave you the 3 farad sort of capacitor, but no matter what the capacitance is, both of these answers are the same. The only thing that would change is how long of time you have to wait before we get to these points.
3 farad capacitor.
Yes.
Okay, and if you see, yeah, we'll talk more about charging and discharging. Basically, when it's discharging, so after it switches to position B, the capacitor is at the instant works almost like a battery to supply the current, the voltage difference across the lamp. So you have some discharging current coming out according to this equation. So discharging current I is equal to C capacitance times dV/dt, which is the rate of change of voltage. So this discharging current flows from the plate where the charges have accumulated into the resistor or the load you have. So then as the accumulated charges flow out, the voltage across the plates decreases. And then once it's fully discharged, as in the voltage across the plates is 0, there's no accumulated charge, there is no more current flow. When it charges, if you see on the graph here, it starts by charging really, really quickly and then slows down. And same for discharging. It starts by discharging really, really, really quickly, and then the rate of discharging kind of slows down. And that is because of this equation. If you're into diffie-qs, you can solve some cool diffie-qs with capacitors and stuff. All right, let's look at this guy. Okay, so discharging current, I is equal to C times dV/dt. So as I've said, it discharges really quickly and then more slowly later. And then it can also, the rate of discharging, the discharge current, the amount of discharge current you have also depends on, no, not the current. Okay, how fast your capacitor discharges also depends on how much resistance you have in the circuit. So there's this thing called time constant, which is the R times C. And this is defined as the time the capacitor takes to discharge 63% of its full charge. So discharge until the 37% of its full charge. And I have these 2 graphs over here. I'll do a quick poll, why not? So these graphs graph how capacitors are charged and discharged. Let's do this poll. That's one question poll. So which of these graphs a charging capacitor? The one at the top, which is 1, or the one at the bottom, which is 2. For reference, you can see over here in the top one, see most of you are getting it right, yeah. As you can see, the voltage is increasing as it charges, decreasing as it discharges. And then this capacitor over here is, we say it's charging through this resistor. So its time constant will depend on that resistance and the capacitance. And this discharging capacitor as well, its time constant will also depend on this resistance and this capacitance. And this is basically, if you notice, this is basically the same thing as the circuit we looked earlier. This one, so when it's at position A, it's charging. There's no resistor in this circuit, but pretend there is. It's charging. When it's at position B, it's discharging, and the lamp or the LED kind of works like a resistor, the load. Okay. So that's capacitors charging and discharging. Looks like most of you got the graphs question right. Do you have any questions so far? Okay. All right.
All right, so a little bit more about capacitors and the sort of real capacitors we'll be using in our circuits. They are pretty small. They have two conductive plates, like we said. In that one question that I went over, we had a capacitor of 4 farads, and Taylor kind of made a joke about it because you're never going to really see a capacitor that is that big. Usually they're very small values. Think of it kind of the opposite of resistance, because resistance you have thousands of ohms. Capacitors you'll be on the other end of the metric scale. And then you have two main types. So you have ceramic ones and electrolytic ones. You have to be careful and sort of know which one you're using, because some of them don't have an associated polarity, like a resistor where you can stick them anyway. You don't really have to pay attention to the direction, but other ones you do have to pay attention to the direction. And you'll notice that on circuit diagrams, it'll have this positive, negative, and this sort of curve symbol designating the negative sign. So just be careful whenever you're using these resistors. Like we said before, they store charge and charge and discharge slowly, and this can be applied in a lot of different ways. So I'm going to go over a few ways on why they might be used. So one of the ways is coupling. So what that essentially means is sometimes you have AC current. If you don't know what that is, it's just DC is when you have a battery that does current one way. AC is the source that switches the direction of the voltage over time. And what capacitors actually do is they let AC current in really well, but block out DC current. So if you have a sort of signal or battery that has part AC but is a DC bias or offset, it could cancel out that DC because it won't let it through. Decoupling. So you could just think of decoupling as you don't want two things to be connected. If you have like a DC source, because the capacitors charge very quickly, it essentially creates an open circuit between 2 points that you don't want current to flow through. And lastly, filtering. So signals or voltages or currents that have rapid time fluctuations, what happens is that when you send them through a capacitor, it sort of averages out these rapid fluctuations, and it sort of can average it to make a filtering process.
Yeah, so the key characteristics of capacitors is they take time to charge and discharge. So this characteristic can be used to do coupling, decoupling, filtering, and stuff. All you need to know, there's a lot of math related to capacitors that you can just go off and do. All you need to know basically for ops is this slide. It stores charge, and then it charges and discharges slowly. And you can get the time constant by using equations. Yeah. And I believe we do have a question here. Okay, let me launch that question too. How many polls today? All right, so here we have more than one capacitor, not just one capacitor, but 3. So on the left-hand side, we have 3 capacitors in series. How do you think the equivalent capacitance will be calculated for these 3 capacitors in series? And at the end of the poll, if anyone who answered right wants to take a stab at explaining the intuition behind it, I'll let you go. So prepare your responses. Okay.
That's everyone.
Okay, that's everyone. All right, any volunteers from the 19 of you who got it right to explain the intuition behind why it adds up like so, like almost like parallel resistors?
Go ahead, Cameron.
Oh,
right.
okay.
So when you got a capacitor, right, its capacitance is inversely related to the distance between the two plates. So when you put multiple capacitors in series, you're effectively increasing the distance of a single capacitor.
Ooh.
It's essentially like having one capacitor that has the distance equal to the sum of all 3 capacitors in series.
That's good. I like that. Yeah, so basically, Uh, the amount of current is constant through all these three capacitors because there's no other source of current coming from anywhere else, right? So we have the same amount of current, and that means we only have this set amount of charges to transfer between these plates of these three capacitors. So we basically have a big capacitor with some distance, like Cameron said. And when we have parallel capacitors, on the other hand, they just add up like so, because, and you can think of this using the water bucket analogy, as we have a picture of this cute cat with the water bucket over here. It's like when you have three capacitors, it's like having three separate buckets, you know? So you can store more charges. So greater capacitance. Okay, any questions so far?
Has this been covered yet for those of you taking Physics 1B? Have you learned about capacitance? I feel like it's still too early. No, yeah.
I think it does come about, and then it's also like some high school physics covers it. But to be honest, I never got it in high school. But now we have ops. All right. As per usual, if you have any questions during the lecture, feel free to type them in the chat. The chat is there for you to type in. Okay, let's go to integrated circuits.
Yes. So integrated circuits are just what they sound. So they're little pieces that have these very complicated circuits inside. Inside your Arduino kits, there is, I think, an L29 bridge. It's those ones that kind of look like they're insects, almost have this like skin sticking out of it. But yeah, so they're complex circuits inside that are very difficult to understand. Most of the times they're really small and cheap, so that way you can get a lot of them. It's, usually not the end of the world if you break one, because you can find them all over the place. And they're usually built for specific functions. Some are timers, some have a certain logic to them. There's op amps, which can do a lot of different things. There's motor drivers in a lot of cases. But at our level and a lot of the levels where you're going to be using them, you just treat it like a black box. So you spend all your time trying to understand every detail about what's going inside, that's going to take out a lot of time. So a lot of times we just treat it as a black box, and we just learn about the input-output relationships between all the pins.
So let's say you want to blink an LED, so you need a circuit to do that.
So let's say you wanted to blink an LED and you didn't have your Arduino to use the delay function. You just had a bunch of parts lying around. Well, you could build something like the 555 timer, which has all these complicated transistors and resistors and capacitors and all this stuff inside. It's very tough to look at, and it would be very tough to make sense out of that unless you're a super easy good electrical engineer. So instead, we don't think about it like that. We try and simplify it, right? So then we have a simpler version here, right? And we got some adders, we have a flip-flop. But even then, that's still kind of tough to understand. I don't want to think about all that when I'm putting this into my breadboard. So we have this nice little thing where we have to worry about only 8 pins and what each of them do. So yeah, we don't have to think about what's going on the inside. We try and forget about it. We just have numbered pins. So on these ones, you'll have to notice that on one side, there'll be this little semicircle and then a dot in the corner. This is to give you an indication about how it's oriented when you compare it to like this picture or whatever data sheet you have, because the pins aren't actually numbered or labeled like they are on your Arduino. In our case, we'll be using a 555 timer for the later project. S3 internal 4,000 ohm resistors.
5K ohm resistors, I'm sorry.
5,000 ohm, even better. Yeah, the 555 timer has 3 5,000 ohm resistors, and you use it for a lot of timing applications. So in a lot of ways, you can replace your delay function in your Arduino. You can use it for a clock, switch, for PWM, something like that. Anything where you use time to sort of space out what you want to do.
Yes, indeed. And then you can run it in different modes for different applications. There are 4 modes that you can run this 555 timer on. It just depends on the circuit you put this 555 timer into. So we're going to be using this mode to create oscillations. So what we're going to do once your part arrives, and we'll do another quick recap of how 555 works next lecture, so don't worry about retaining this information. I wouldn't be able to. So what we're going to do is in astable mode, the 555 timer outputs oscillating square waves. And that basically is just oscillating square waves as we've seen before. So it's high, low, high, low, high, low, high, low until you reset it or do something about it. So it'll output low when the voltage at the trigger pin over here is less than 1/3 of VCC, which is the power. And then it'll output high when the voltage at the trigger pin is greater than, I have so many typos today, is greater than 2/3 VCC. So depending on what the voltage at the trigger pin is, it'll output low and high, and that's how we get the oscillating square waves. And the frequency of these oscillating square waves is determined by the capacitor's time constant. So we have a capacitor over here because, as you see, we want the voltage we see at the trigger pin and the threshold pin, if you notice they're on the same node, to change over time, but not like all the time, you know, we want it to change in some fashion, some predictable fashion. So we use a capacitor to do that because guess what capacitor does? It charges and discharges slowly over time. So what we have is once the voltage at this plate of the capacitor is charging, we see that the output voltage is high. And when it's discharging, we see the output voltage is low. Yeah. Okay. And we'll do more on the 555 timer. We'll talk more about this next lecture as well. I guess, do we have any questions so far?
There was one about what happens between 1/3 and 2/3.
Oh, that's when the capacitor is charging or discharging. So once that threshold, the capacitor is always charging or discharging. And once that threshold, the 1/3 and the 2/3 are hit, the circuit, the 555 does things to let the capacitor either go from charging to discharging or discharging to charging. Does that answer your question? We'll see like or schematic next time, and it'll probably make more sense with all the resistors in place. This is how it looks, but it'll look more like a circuit next time. All right, I will stop the recording, not stop share. I guess I'll stop share too. Stop